Hi all, this is Mr. Yeager for Honors Chemistry, and we are looking at molecular bonding today. We'll get into more about shape in the next video, mainly going over how to draw Lewis structures for different types of compounds today, which might take a little bit of time. So here we go. Okay, so here we go. We're going to look at single versus multiple covalent bonds and how that's formed. We're going to look at VSEPR, okay, that'll be actually in the next video, and molecular shape and bond character. So we're only covering the first part today, single versus multiple covalent bonds and how to draw those out, okay. Intermolecular forces will also come up in the next video, okay. So we've already talked about covalent bonding. We talked about how to name and formula right for these, but now we're interested in actually going, well, what do these covalent structures, these molecules actually look like? Okay, so that's what we're looking at on this part. So we can figure out exactly how they're bonding by. Basically, we want to figure out how many valence electrons the atoms already have. All right, this is kind of a process that we can use to figure out the number of bonds between these elements. So determine the number of valence electrons the atoms already have. Find the number of electron atoms in the compound want. Okay, and then we do the number of electrons wanted. And again, wanting is, we know all atoms want to have 8, other than hydrogen, which would have 2. So number of total electrons that the compound would want, based on all the atoms, minus the number of electrons that they have, divided by 2, and that'll give us the number of bonds, okay, in our molecular structure, okay? So how do we draw out Lewis structures? So we determine the number of atoms of each element that are present in the molecule. We write the electron dot notation down for each type of element, okay? And then we determine the total number of valence electrons in the atoms to be combined. So again, we're kind of reviewing what was on the prior page, okay? You arrange the atoms in what we can call a skeleton structure of the molecule, putting the least electronegative atom in the center, hydrogen being an exception because it can only form one bond, and then connect the atoms with a bond by drawing a single line connecting the elements, okay? And so that's what we're going to call a bonding pair of electrons. We then go back and add all the unshared pairs of electrons so that each atom can basically have 8 electrons surrounding it. Okay? So that's what we're looking at with it. All right? So the last thing is count the electrons in the structure to account for the total number of valence electrons calculated. If too many electrons have been used, subtract the electron pairs by changing non-bonding pairs to bonding pairs until all valence electrons are accounted for. All right? So anyway, I mean, that's a very large instruction. Basically what we're going to see is I can figure out, based on the Lewis dot diagram with the dots, to be like, okay, this object wants this many bonds, okay, based on the number of lone pairs of electrons that it has. Not lone pairs, sorry, single electrons it has, and then combine it with the other atoms that are present. The whole subtract the total number of electrons that it wants minus the electrons that it has, divide by 2. That can then help us figure out the actual number of bonds that we need to do. Okay? So, starting off with basically single covalent structures. Okay? So, if I start off with hydrogen, H2, again, we talked about them being diatomic. I have hydrogen with one dot and hydrogen with one dot. All right? The idea is both of these hydrogens want a total of 2 valence electrons to share, and that'll make each hydrogen atom happy. Okay? Is basically what we're looking at. If I go off of my little idea of the number of electrons want, basically in this molecule, I want 4 total electrons. How many number of electrons do I have? I only have 2 electrons. So if I subtract the 2, it's 2 divided by 2. Again, I end up dividing the difference in the electrons by 2. This is telling me that there's going to be 1 bond in between them. So, ta-da, we basically just connect those dots, and then we have that bond. And we show that. This line here is basically representing 2 electrons present. And so the idea would be, if I kind of cover up one of the atoms, 2 electrons are on this hydrogen, and if I cover up the other atom, 2 electrons are on this hydrogen. So they both have those 2 electrons now. Okay? One thing to kind of realize, hydrogen always wants 1 bond. Hydrogen can only make 1 bond. And same thing go with the halogens. Halogens can only need one bond and they'll be happy. So why for that for chlorine? It has 1, 2, 3, 4, 5, 6, 7. The other chlorine has 1, 2, 3, 4, 5, 6, 7. And again, you can see that we're going to combine those two, that they'll share. So this is called a bonding pair. Okay. And then all of these on the outside of the atom, they're called lone pairs. Okay. So that's what we mean by bonding and lone pairs. Bromine would look the same. I'm already just going to kind of do it. Bromine only needs one bond. There we go. Okay. So sometimes we don't have to do this process over here. We don't have to do it. It will prove that we only need one bond for every single one of these molecules, but it doesn't have to be done that way. Okay. All right. What about some molecules that might have multiple covalent bonds? In other words, they might form more than one bond in between them. Okay. So if we look at oxygen, oxygen has 6 electrons. 1, 2, 3, 4, 5, 6. And this oxygen has 1, 2, 3, 4, 5, 6. Okay. Again, this one's pretty straightforward. We can kind of see it that, hey, these 2 electrons will share and these 2 electrons will share. We then draw it like this. We draw those 2 bonds in between, and then we draw the extra electrons around it, the lone pairs around it. But this right here is called a double bond. A double bond. All right? And that's going to be stronger than a single bond because obviously they're sharing more electrons between them. If I do my little formula, want, have, and again I'm dividing by 2, I want 16 electrons. Both atoms want a total of 8, so I want a total of 16 electrons. I have 12. 16 minus 12 is 4, divided by 2, 2 bonds. Okay, so I run into that again. For the bottom one, nitrogen. Nitrogen, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. For nitrogen, again, I feel like you can pretty much see this one happening, where we get 3 bonds between the nitrogen atoms because it has 3 lone electrons, not lone pairs, but lone electrons. All right, and so therefore we get a structure like this. Okay, where each nitrogen now is showing it has a total of 8 electrons on it if they both completely share those bonds. All right. So kind of as a general rule of thumb to kind of go with is this, at least so far, is again hydrogen and halogens form one bond. All right. O group elements, so oxygen, sulfur, selenium are the main ones we're going to run into, have 2 bonds. And the N group, which usually the main ones would be nitrogen and phosphorus, but you could find arsenic in it too. They like to form 3 bonds. Okay. Now it doesn't mean that they form a triple, like 3 triple bonds. That would not make any sense. It doesn't mean that these groups have to form a triple bond. It just means that they might need 3 single bonds, or a double and a single bond. They just have to have a total of 3 bonds on the atom itself. All right. The other group I'm ignoring, but we'll probably see in a moment. The C group. C has 4 valence. It needs 4 bonds. So C can form triple bonds, single bonds, and double bonds, depending on what it's with. Okay? So here we go. So let's practice some. So what we do here, again, kind of taking this to an extreme, like not extreme degree, but to every single step that was mentioned, I technically draw out each of my atoms. So there's the C. I have 3 H's. And then I have an iodine. All right, and again, we should be figuring out the number of dots around it very, very quickly at this point. Okay, so, I mean, again, you can probably look at this and go, well, C will go in the middle. It'll bond with the H, all of the H's once, and then the iodine. And there you go, and then I have to do it the rest of the electrons around the iodine. That right there is the correct structure, okay? And we'd call this the electronic structure. That's the name that we would give it, where you just kind of block it on around there. This is called the electronic structure, okay? Or electronic Lewis structure, okay? So we don't bend any bonds or anything like that yet. I'll come back to that later. But that's basically it. Again, the way I kind of look at this, I know it says the element with the lowest electronegativity goes in the middle. A lot of times it's the element that wants the most bonds will generally go towards the center. Okay, clearly you can't have hydrogen in the middle because it's only going to form one bond, so that's not going to work. Okay, if I do my little formula, want, have, let's do want, or sorry, have. I always do usually have first. So I have 4 plus 5 plus 6 plus 7, and then 7 plus 7 is 14. So I have 14 valence electrons available. How many total electrons do I actually want to basically create a full structure? That would be 8, 2, 2, 2, and 8. So that adds up to 22. So 14 minus 22 is 8 divided by 2. We're going to have 4 bonds in my compound. Okay? All right, so let's just do another one. All right, I'm going to do all the steps again. We got N right there, and then I'm just going to write 3 of these. I'm not going to draw all of these out. There's just so many dots. Okay, and so again, we should notice this is a halogen. Each one wants only 1 bond. We have the nitrogen. It wants 3 bonds. What's going to happen? It's going to go 1, 2, 3. Keep that lone pair. And then we also have to put in all those other dots. So again, sometimes the annoying thing with these is just drawing a bunch of dots all the time. But there you go. Every single element on here has 8 electrons. This fluorine has 1, 2, 3, 4, 5, 6, and a bond. A bond means 2 electrons, so that's 8. This one has 8. This one has 8. The nitrogen has 8. So it's all good to go. Okay? H2SE. SE would go in the middle, and I'd have H on either side. 1, 2, 3, 4. Again, it doesn't have to be that way. You could draw it this way too. SE, H, H, depending on how you do your dot structure. But that would be it. Okay? And again, I'll show you the have and want again. I have hydrogen each has 1, so 2 times 1, and this one has selenium has 6, so I have 8. I want. This would want 8, and this would total 4, so 12. And so 12 minus 8 is 4, divided by 2, 2 bonds. So again, this is a method if it's necessary, which it will be in some cases. We will get to more difficult ones along the way. So how about this one already? There's a good example. C2H2. Okay? So with C, it's 1, 2, 3, 4. C, 1, 2, 3, 4. H1, H1. Okay? And so this one might be a little tougher to see because it's like, okay, does 1C take both the H's? That doesn't make much sense. You know, we could start playing around and being like, you know, this will be H, and this will be H, and this will be C. But then I still have that electron, I have that one, and that one. It's like, wait a minute, is there a double bond? But I can't leave this. I need to get 8 valence electrons around it. So this might be one of the first ones we try to do our want and have. Our want and have. So I have 4 plus 4 is 8 plus 9 and 10. So I have 10 total electrons. I want 8, 8, 2, 2. So that would be 16, 18, and 20, right? Yeah, 20. And so 20 minus 10 is 10 divided by 2. Again, don't forget to divide by 2. I'm going to have 5 bonds. You might be going, well, how the heck do I get 5 bonds? All right. So what it comes out to, and again, you can play around with it quite a bit. You can start figuring out that, hey, we're going to have to connect both those C's together. All right. And maybe each of them should take just 1 hydrogen instead of what I did the first time where I gave 2 hydrogens to 1 atom. Well, the thing is, that's 3 bonds. I need 2 more bonds. Well, why don't we just form 2 more bonds between carbon and carbon, make it a triple bond. And right there is your structure with no lone pairs. All right. Nope, I don't know why I drew that all out. Sorry about that. I was trying to do this. If I look at this hydrogen, let me get rid of some of these lines. Okay. Sorry. Let me draw that out again. So H, C, dot, 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 C, H. If I now look at any individual atom, they're good to go. H has 2, H has 2, this C has 8, this C has 8. Is the correct structure. Yay. Okay. C2H4, sure, let's do that one. I'm going to start skipping some. I have a lot in here, but there, we can kind of start skipping some of them here. So C is 1, 2, 3, 4. C 1, 2, 3, 4. H, I'm just going to write 4 H's. All right. As you can kind of tell from the last one, again, let's do the have and want. So I have 4, 8, and 12. I have 12 electrons that I have. How many do I want? 8, 8, and then 4 times 2 is 8, so total of 24. In this one, I'm going to have 12 divided by 2. I'm going to have 6 bonds present. All right? And as you can kind of tell here, we don't want to just surround a carbon with all of the hydrogens. That's not going to work. So let's connect the 2 C's and let them share 2 of the hydrogens. Let's put 2 right there and 2 right here. Okay? And then what's missing? H's are all good, but the C's only have 3 bonds. There's a 4th bond. Okay? And if I count them, or sorry, a double bond, a 4th bond for each C. And I count it up, 1, 2, 3, 4, 5, 6 bonds present. Okay? So, I mean, this continues on and on. I'll show another one. I know it's good practice, but you can just keep on looking at some of these other examples along the way. Okay? What I might do is I might just draw out what it looks like, and you can go back and kind of go through the have and want and everything like that. So for this one right here, it would be N double bond with an O, single bond with an F, and I get 1, 2, 3, 4, 2 right there. And that would be my structure. There'd be 3 bonds there. Okay, NOF. All right. So again, you got to be careful with this sometimes, where we got to just make sure that you are including all the dots and that you continue to move forward. All right, sorry about that little break there. This one right here, this one will look like this. We would have C, H, oh, let me draw this the right way. H, H, and then a double bond to SE. 1, 2, 3, 4. Okay? I'll go and show just why it should have 4 bonds. We would have, there would be a total of 1, 2, 5, 6, 12 electrons present. How many do they want? It would be 8 plus 8 is 16. 2 is 18. 2 is 20. So 20. 8 divided by 2. 4 bonds there. Okay? I do a lot of examples with my students. This one should look like this. BR, BR, BR. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay? Again, some of these you will notice right away. I don't think you would have that much of an issue. Phosphorus should have 3 bonds, bromine each want 1, so why don't you put it all around the phosphorus? Okay. C2H3N. Ooh, let's look at this one. C2H3N. Ah, I know it now. Okay, so this one's a good one to kind of take a look at. So this is where this one's not as obvious to see. So you got 2 carbons, we got 3 hydrogens, and then we got 1 nitrogen. Okay, and maybe you do see it right away. Good for you. Okay, how many electrons do I have? I have 8, 9, 10, 11, 16. 16 electrons. How many do I want? 8, 16, 18, 20, 22, and 30. I want 30 total electrons, basically somehow shared between them. So that would be 14 divided by 2. Ooh, I want 7 bonds. So that's kind of a weird one in terms of an odd number. Okay. So what would this end up being? Okay. We would absolutely want to basically put a C in the middle. Okay. I'd put the other C next to it in the middle. And what we can kind of come out of this is I could put H, H, H around the C and then do a triple bond, triple bond to the N. Ta-da. Ta-da. Okay, and there we go. That would work. All right, that would be my molecule on that one. Any questions? Any questions? Nobody's going to answer me. Okay, but that's basically it. Okay, oh, I need 2 dots there. Very, very good. All right, I'm going to kind of leave these other ones alone, and we're going to move on to something else. What if I want to sketch a Lewis structure for a polyatomic ion? For a polyatomic ion, it's the same process, okay? But the total number of electrons will be adjusted based on the charge that I have for it, okay? Is what I'm looking at there. Okay, so the same idea, except then now you're going to have to pay attention to the charge of the atom and add that into it. If it has a negative charge, we're going to basically add that valence electron to the total number that you have and that you want. If it's positive, you basically subtract that, okay? So that's what we're going to run into here. We still do the same idea. We write out the skeleton structure and go from there. So these, again, I feel like you do run into some more interesting, weird setups, okay, where we'll have these extra electrons where it doesn't seem like it's right. Like you might have a single bonded oxygen and so forth because that extra electron's completing the lone pair. So if we look at hypobromite here, okay, what we would be doing is we'd have bromine as 1, 2, 3, 4, 5, 6, 7. Oxygen is 1, 2, 3, 4, 5, 6. And then we have this one extra electron from the negative charge, okay? And so what that means is I have 7 plus 6 is 13. I have 14 electrons, okay? How many do I want? Okay, how many do I want there? For my atoms, in this case, I would want, what is that, 16? Okay, 16 electrons, all right? I don't include the extra electron in that, in the sense that, hey, these atoms want 16 to be happy. They'll have their full octet with 16. So what I run into here is this is equal to 2 if I subtract, and if I divide by 2, that means there's only one bond between these two. So you're going, that's weird. I understand bromine having one bond, but oxygen having only one bond, okay? And so what happens here is bromine will go ahead and share that one electron. It looks good. Technically, you could sit there and be like, oxygen still would only be left like this, because again, one of the electrons is shared, but not the other one. But this is where that extra electron comes in, that negative charge. We add an additional dot for that extra charge, and we usually then put these things in brackets and say -1, okay? Or minus. It could probably just be left as minus, okay? But that would be my structure for this polyatomic ion of hypobromite. Okay, so a little bit strange, but it's clear. I mean, if you look at each atom, there's 8 valence, so it's all still good to go. We are good to go with that. Okay, so it's definitely a little bit strange. It's definitely a little bit odd with it. For BrO2, that would be bromine has 7, and then we got 2 oxygens. They have 16 total, and then plus 1 more electron. So how many do I have? I have 24 electrons to use. How many do I want? Well, 3 times, oops, no, I screwed that up. Sorry. This has only 12. That only has 12. So 19, 20. That's what I was just looking at. I was like, that didn't make sense. It has 20 electrons. They want a total of 24. So this comes out to 4 divided by 2. This is going to have 2 bonds. Okay, 2 bonds involved with it. So where does this come from? Okay, basically we got something that kind of looks like this. We got bromine forms with an oxygen, forms with another oxygen. Okay, so that oxygen's all happy. This bromine's all happy. It's this last oxygen that's a little bit odd, but all it would have is basically it would have that extra dot from the negative charge, and there you go. Okay, there is our formula. Okay. Again, a little bit odd, but you gotta just kind of trust it. Cyanate. For cyanate, we got carbon. It has 4, nitrogen has 5, oxygen has 6, and then I have 1 extra electron. So how many do I have? 9, 15, 16. How many do I want? I want, in this case, 24, right? Yep. 8, 16, and 24. This subtracted 2, that's 8, divided by 2 is 4 electrons. Okay, or 4 electrons, sorry. 4 bonds. Gets a little bit repetitive, doesn't it? 4 bonds. So what would this one look like? I'd put carbon, again, basically in the middle. In this case, I know you might be thinking it's different structures, but basically it would look like this in this case. Okay, where we got C in the middle, triple bonds to the N on one side, and then the O is what's left over. And we have a -1 charge, -1 charge in the end. Okay, we got to form those 4 bonds. I'm sure you're sitting there thinking, you know, well, why can't I do like this, where it's like 2 on this one and then 2 on this one, and that would make that one all okay, and then why wouldn't this one then get the extra electron or so forth? Okay, that's a little bit tough to answer, but I mean, again, it kind of goes with, in a way, the name of it, in terms that it's cyanide, so we know we're going to have that CN together. Okay, and I mean, even if I look at this, let's double check this real fast. I mean, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 16, 18, 20. I mean, do I have a total of, I have 2, 4, 6, 8, 10, 12, 14, 16, 18. And so I think that's the other issue we run into, is whether we have the correct number of bonds that basically are present there in some ways. All right? So that's another thing to kind of pay attention to with it. Okay? Phosphite. Phosphite, phosphite, phosphite. Okay? For phosphite, we got P is 5. O, they each have 6 times 3. So there's 18, 23, but plus 3 more electrons, so I have a total of 26 electrons. How many do I want? 8 plus 24 is 32. Okay? So then I have 32 minus 26 equals 6 divided by 2 equals 3 bonds. Okay? 3 bonds. And again, this is kind of weird where it's just like O, O, and O, and then each of those gets an extra electron on it. All right? So that's what we're looking at there a little bit as well. All right? All right, I want to go back to this one real fast. I did misspeak there. So we had that this was N and then O, okay, as our structure, dot, 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 and then dot, dot, minus 1. All right. This is an allowable structure as well. Okay, this would actually work out okay. All right. This, I was getting ahead of myself there a little bit. This is a situation which I'm going to mention at the end of this talk of what's called resonance. Okay, and I might have to jump to it now and then come back with a couple of the other structures. This is where basically these electrons being shared over the molecules are basically traveling back and forth around the carbon and around all the atoms. Again, when we say they're shared, they are truly shared amongst all the atoms. So they could be anywhere within the molecule, essentially, at that point in some way. And so in the resonance structure here, we actually, if there's more than one allowable structure, we call that resonance. Okay, so I do apologize for that mistake real fast. So I'm going to jump straight to that with this. What is resonance? It occurs when there's more than one structure, but essentially identical, and they're both correct. Okay, and again, it illustrates that those electrons are delocalized in a molecule and can move freely among all of the atoms. So you can see the one I have down here. I just got ahead of myself by having CNO on the presentation, but it's the idea that all 3 of these structures are essentially the same. It's just, quote unquote, which oxygen atom has the extra bond. And you can see how we draw this out. We draw each one in brackets, and you draw these arrows going both ways, because the idea is all 3 of these are existing at the same time. All 3 of these formations of the atom are existing at the same time. And it's not just that you're rotating the atom, it's that oxygen atom has, quote unquote, a double bond, like this one has the double bond, this other oxygen has a double bond, and this other oxygen has a double bond. So it's definitely a little bit odd there some, okay? So let's see if I can go back and show any more of those. So here's a couple with that, okay? So O3, okay, oxygen 3. That basically means I have 3 oxygens, so I have a total of 18 electrons, but I want a total of 24. So this comes out to 6 divided by 2. We're going to have 3 bonds between this O3 molecule called ozone. And so what happens here is I could have it this way, okay? This way working with it, 1, 2, 3, 4, okay? Basically 1, 2, and then 1, 2, 3, 4, 5, 6, okay? Essentially looking at it that way. 2, 4, 6, 8, 10, 12, 14, 16, 18. Yep, see, I mean, that all works. Or it could be the other side. Okay, the other side. So that is an example of a resonating structure that we got there. I'm going to do one more, and I think I'll call it at that point. If I do NO2, N has 5, and then I have 12 plus 1, so a total of 18 electrons in NO2. I want a total of 24. So 24 minus 18 is 6, divided by 2 is 3 bonds. And what I run into here is kind of the same, kind of a similar situation where one side is double bonded and the other side is not. But it has that extra electron now. Okay, but this one I would say is negative, and then my other form of it would just be where the double bond's on the other side. Okay. So that is resonating structures being involved there. So again, we kind of jumped it a little bit early. I made the mistake of saying that you can only have it this way because of the name. That was junk, sorry about that. All right, I kind of looked at it and was like, this is something up with it. I didn't pay attention. So I'm glad we caught it. So we do have the opportunity that we might have resonance structures. And if you do, you need to draw all of the possibilities. They are not super common, but if you run into it and go, hey, this is right and this is right, draw both of them out. All right, we are done. Thank you.